So this work is part of the PhD of Adil El Abdouni. We defended this PhD at the beginning of the month, and it was co-supervised with Bertrand Chloé.
Ton micro qui n'est pas allumé.
Non, je vais l'avoir allumé. Ah, si, c'est bon?
Ah, voilà.
Si, si. So together with Bertrand Chloé also, and it has been made in the framework of the ANR NOLO. And also the ERC project Singer, edited by Sylvie. So in this work we use, the method is strongly based on previous work we obtained, previous results we obtained with Claudia Fonte and Stéphane Michelet also. Okay, so the topic is the time periodic non-local equations with drift. So I will write the equation. It's a partial differential equation of the transport type dtu of tx plus the divergence of in x of u of tx plus times the vector field v of tx, and it is equal to a of tx u of t x plus some non-local term, kernel term, the integral over all the whole space Rd times q of ty x u of ty dy. So this non-local equation of the transport type can model, for instance, the dynamics of a population density u of tx of individuals which are structured by the trait x, and this zero-order term represents, so A is the fitness parameter, it's the balance between birth and death, and this term will select the individuals with the trait for which A is maximal. The integral term stands for the mutations, okay, the creation of individual of trait x starting from individuals of trait y. And concerning the drift term, it can model the fact that we consider an environment which moves a long time. For instance, the maximum of A can shift, and following this movement in the moving frame, this makes appear a drift term in the opposite sense of the movement. So in this moving frame, where it is expected that the coefficients do not depend on time anymore, but in this talk we also consider additionally to the movement of the environment some fluctuations which are assumed to be periodic in time. So we assume that V, A, and Q are T periodic, so with the same period in the T variable. Okay, and the question is, what is the behavior of the solutions to this equation? I mean, the asymptotic behavior. How does behave the solutions when time goes to infinity? So due to the periodicity of the coefficients, we expect some kind of periodicity in the long time, but not exact periodicity because this equation is non-conservative. Okay, due to the source terms here, the creation or degradation of individuals and the mutations, there is no conservation of mass or any quantity. So we expect some growth of the population or decay of the population, depending on specifically the sign of A. So we expect something which grows or decays exponentially fast with a parameter which I call lambda f in reference of for periodic matrices. So this kind of behavior, exponential Malthusian behavior, modulated by some periodic function of x, periodic in time, and due to the linearity of the equation, we expect we need some linear influence of the initial data, which is given by a linear form, phi 0, u0. So u0 is the initial data, and phi is a linear form on the space. It will be L1 in this talk. Okay, so the question is prove existence of lambda f phi 0 ft family ft and phi 0 such that so lambda f is the Malthus parameter, ft is periodic in time, so this family is T periodic, and exponent. This limit must be a solution of the equation. So if the function which maps t and x to exponential minus lambda f, no, exponential lambda f t times ft of x, solution of the equation, this equation. So this is what we want to prove. So the existence of the triplet and convergence. Like this kind of convergence. So what is the method we'll use? So we associate to this equation a family of operator, family indexed by 2 times t and s. So t is larger than s positive, such that the solution started from us at time s is the solution to the equation starting from us at time s. So this family of operator is well defined for this kind of equation, and it has the semi-flow property. So if I write st3 t2 st2 t1, okay, so looking at the solution at time t3, starting from the solution at time T2 at time T2 starting from T1, it's the solution at time T3 starting from T1, and the periodicity of this, it has T periodicity property, which is that for all S and T, looking at the dynamics between S plus capital T and T plus capital T is equal to, it's the same dynamics as between S and T. Okay, so we set capital S, this operator between the time capital T and initial time 0, and we perform a spectral analysis of this operator S. Okay, so to do so, we will use an abstract result about operator theory. So we take an operator S in the space L1, which is positive, meaning that it maps positive, non-negative functions to non-negative functions. And we assume that for some integer k and some positive number kappa naught, we have three assumptions. The first one is that we have some kind of super solution. So there exists G naught in L1 plus but not 0, such that S G naught is larger than kappa naught G naught. Second assumption, that we can write the operator S to the K, some iterates of the operator as we can decompose, split him as the sum of W plus K with the norm of W smaller than kappa naught to the K and capital K weakly compact. Meaning that it maps bounded sequences into weakly compact sequences in L1. We also suppose some strong maximum, some strong positivity condition, meaning that for all f in L1 plus not 0, SF or SKF, it's enough, is strictly positive for almost every x in RD. Okay. And we will denote this strong positivity condition as SKF strictly positive like this. And under these assumptions, we have the existence and uniqueness of a real number lambda 0, f0 and phi 0 in R times L1 plus times the dual space L infinity plus, such that S f0 is equal to lambda naught f naught, S star, the dual operator, times phi naught is the lambda 0, phi 0, and some normalization condition for ensuring uniqueness in particular. We assume that the norm of phi 0 is equal to the duality bracket between phi 0 and f 0 is equal to 1. So it's the existence and uniqueness of principal eigenfunction and eigenvalue and eigenfunction for this operator S. We will use this and also the fact that lambda 0 is strictly positive. F0 and phi 0 also strictly positive in this sense. And the stability result that there exists C positive and zeta positive, zeta and 0, 1, such that for all initial data f in L1 and for all integer n, if we normalize S by 1 over lambda 0, we get that these iterates converge to the projection, spectral projection, onto F0 exponentially fast. Okay, so I will give the idea of the proof of this theorem. In the case k is equal to 1 for simplifying the notations. So why this result is true? First of all, I didn't mention this. So S is an operator in L1 which is bounded. Okay. So the fact that S is bounded means that the spectrum of S is inside a ball of radius, spectral radius of S. And the first assumption guarantees that this radius is larger than kappa 0. Okay. The second assumption ensures that since the norm of W is less than kappa 0 to the k, here k is equal to 1, this means that there is another ball here with radius norm of W. And inside this ball, we don't know anything about the spectrum of S. It can be a continuous spectrum, something we don't want to look at. But outside of this ball, due to the assumption that K, capital K, is weakly compact, this ensures that we only have eigenvalues, symplectic spectrum, with eigenvalues of finite algebraic multiplicity, isolated, infinite number. And in particular, the spectral radius of S is an eigenvalue. This is classical fact of the positive operator. For a positive operator, the spectral radius is inside the spectrum, and since here the spectral radius is larger than the norm of W, it must be an eigenvalue. So this ensures that we have lambda 0, which is actually the spectral radius of S, and the existence of F0 and phi 0. Okay, and the third assumption guarantees that F0 and phi 0 are strongly positive, okay, in this sense. And also the uniqueness of the eigenvalues. It means that actually the lambda 0 is an algebraically simple eigenvalue. So it only remains to prove the convergence here. And this is a consequence of what we want to prevent here is that is the existence of eigenvalues with on the circle here. Okay. For now, we cannot prevent this. We did not prevent this. So why it cannot happen? It's because if you have an eigenvalue here, we are able. So first, we prove that the set of eigenvalues with the modulus equals to Rs is a group for rotation. It means that if this is an eigenvalue, this one will also be an eigenvalue with the angle here, which is twice the angle here, etc. And since we must have only a finite number of eigenvalues outside of the ball with radius norm of W, this means that this is a finite subgroup of the circle. More precisely, it must be unity of it must be root of the unity times lambda 0. So if we have one eigenvalue here, iterating the operator, we can build from the real part or the imaginary part of the eigenfunction another eigenfunction associated to lambda 0. And this contradicts the uniqueness of the solution because if we have another eigenvalue, the eigenfunction associated to this must satisfy, if you have here F1, it must satisfy this. Okay. Because the eigenvalue is not lambda 0. And from F1, we can build another solution to the eigenvalue problem for lambda 0, and this contradicts this because the only one must satisfy it is not orthogonal to phi 0 because we have normalized this like this. So this means the message is that there is no eigenvalue, there cannot be eigenvalues with maximal modulus. Okay. So if we don't have this eigenvalue, yes.
Can you explain why it's a root of unity?
Yes.
It's exactly why is it a root of unity and not like why is it rational?
No, because it's outside of this ball, we only have a finite number of eigenvalues.
Yeah.
So if
it could be an irrational.
no, because of the group structure, if you iterate, if it's irrational, you will.
Group structure. No. What is it?
It's a group. Okay, if you normalize, you set S tilde is equal to S. In this case, the radius is 1, and it's a group for the. It's a subgroup of the circle for the multiplication. So finally, we don't have any due to the uniqueness. Again, it's the uniqueness which makes it work. No, it's not easy. No, it's not easy. It's the idea of the proof, but there are a lot of work. Even for proving that.
If it would be rational, you can make.
You get an infinite number. Yes. Okay, so even for proving that this is an eigenvalue, actually we use the assumption 2. It's a construction. Yes, a lot of things hidden in this picture. But the idea is then that because there is no eigenvalues with maximal real part, we can find another circle here, strictly smaller than the big one, and so we have here what we call a spectral gap. It means that outside of this red ball, there is only lambda 0 as an eigenvalue. So if we define the subspace phi 0 orthogonal as the function of in L1 such that phi 0 f is equal to 0. So it is stable subspace under S. Okay, and in this set, in this subspace, lambda 0 is not an eigenvalue because f0 is not in this space because of this normalization. So lambda 0 is not in the spectrum of S in lambda 0 orthogonal. This means that the spectral radius of S phi 0 orthogonal is strictly less than some psi lambda 0. And here the spectral gap will be 1 minus psi lambda 0. Okay, this distance for some psi between 0 and 1. Now we can use the spectral radius formula, which says that this is the limit as n goes to infinity of the norm of S in this subspace to the n, 1 over n. And this guarantees that the norm of Sn lambda 0 minus n Sn of in L1 is less than C times psi to the n for some C positive and for all n So this means times the number. So this means that for n large enough, because psi is, zeta is less than 1, for n large enough, this operator is a contraction in this invariant subspace. Then for f in L1, we have that f minus the projection is in phi 0 orthogonal, and then this immediately implies this convergence. And then we can go from this discrete convergence to continuous time day convergence, because there is nothing bad happening between the period between the time 0 and t, capital T, so that we can also prove that exponential minus lambda ft s t 0 f minus where lambda f is the log of lambda 0 divided by capital T, and ft is nothing but exponential minus lambda f t s t 0 f 0. So this is well capital T periodic because of the solution of the definition of f0. Okay. So I will only give the assumptions on the coefficient of the equations which allow to apply this theorem, and it will be. So about the vector field V, we assume, for instance, that it is globally Lipschitz, that we can define globally the flow xts of x as a solution to dtx ts of x is equal to V of tx of ts of x. So this OD is well posed, and with initial data. And we assume that the trajectory of this characteristic equation doesn't stay inside the ball uniformly in the initial position x. This means that the supremum in x of the measure of the time starting from initial data, initial time 0, so the trajectory stays a finite time uniformly bounded with respect to initial position inside the ball of radius for any radius. Okay. For A of tx, we assume that it is a L infinity lock and confining in the sense that the essential supremum in T and x larger than r of a of tx This means that a goes to minus infinity uniformly with respect to time and yes, uniformly with respect to t.
Question. So the first one, does it mean that you have no stationary state in particular for your?
For the flow, no, there is no stationary state.
Okay, you must go to infinity.
Yes, the typical example is drift with speed 1 in one direction, for instance, in x1.
And periodic one.
And
An example which is periodic.
for v,
Not trivial, yeah.
for v, 1 plus cosinus t.
Okay.
So, yes. Yes, well, typical example is this. V of tx is equal to 2 plus cos t in the direction and for q, we need some positivity assumptions. So q of tx, we assume that it's continuous in time, bounded from r plus, from r, actually it's periodic, so from r in L infinity of rd with value in L1 of r. Q of t yx. Okay, so y is the initial position, and it creates individuals with trait x. This distribution in x is in L1, a finite number of new individuals, and it is bounded uniformly with respect to the initial trait. And we also assume some non-concentration condition, which is that for any epsilon positive, you can find eta positive, such that for any trait space capital E, which is small in measure, the big measure, uniformly in time and in y, the integral, the number of individuals with trait x in this set E is less than epsilon. We don't charge small sets. And this is a non-concentration assumption. And the positivity condition is that exists Q0, R0 positive, such that for all t, Q t yx is larger than Q naught. So for traits which are close, with distance less than R0, there is a probability for going from y to x given by Q0. Okay. So with these assumptions, we can prove that the semigroup, I also have to define the semigroup, semiflow. So we start from the equation So if we don't consider the integral term in the equation, it's a transport equation. We have an explicit semigroup, explicit semiflow. Capital V of Ts. We set B, T, F of x, the integral term. And the UML formula reads STS is equal to V with S is equal to 0. ST0 is equal to VT0 plus the integral between 0 and t of STS B SV S0 ds. Then we take t is equal to, so s to the k. I'm going to apply this with for k large enough. S to the k is equal to s k capital T0, so it's equal to v k. It is all something which is this, which will be w plus this, which will be compact. So we take k large enough. So k is chosen large enough so that w is has a small norm, small enough in the sense that it has to be less than kappa 0 to the k. So the first assumption is satisfied by using, in particular, this strong positivity condition on the kernel. Then the second one is obtained by considering k large enough using these two assumptions. The trajectory go outside of the balls, and outside of the ball, the fitness A is a strong depth rate. So this ensures that this operator, which is a solution to this equation, so we have a drift with a strong depth rate outside of the ball, it will be small in norm. And then we prove that this is compact by combining, again, these two assumptions for V in order to get tightness of the family. And then using B and this non-concentration assumption to prove narrowness of the family. So this prevents escape to infinity. This prevents concentration. We have, by Dunford-Pettis theorem, weak compactness of this operator. We can apply this, and we get the conclusion. And so that, just one word to finish. There is also some Harris-type conditions which allow to quantify these quantities, because with this method we have no idea of the value of C and zeta. Thank you.
Thank you, Pierre. So, any question in the room?
Yeah, that's right. I heard once about the notion of Floquet bundle. I don't know if you are familiar with, and my question is whether there is a possibility to extend to a very, very general...
This is the natural next step to extend this periodic setting to general time inhomogeneity, and to prove to extend results that exist, to my knowledge, for Floquet bundle only for diffusive processes to this kind of non-local equations. Yes, it should work. I think so. Because when you have the result for time periodicity, you can use the same approach as Ushka and
Hi, I'm just wondering if you impose some boundary, so then you have some, instead of having it like just RD, you have some subset of RD with some boundary condition, maybe Dirichlet, Neumann, whatever. Like, how much of what you've done would just carry over in the same way? What would be the exit?
Actually, if we have a bounded domain, for instance, with Dirichlet boundary conditions, it's either simpler because this assumption, it can be written as outside of the domain, A is minus infinity, so it's even stronger than this. And the only assumption we need is to replace this by the trajectory must go outside of the domain. In this condition, it works the same. If we have Neumann, it's more tricky. It's not...
Okay, thanks.
Yes.
Any other question? So just one. So the zeta here is definitively not constructive, But for this model, you are able to make things constructive or not?
Yes, if I had time, but if it's in the question, I can write the conditions. So we can add, under the same assumptions on the coefficients, we can verify other Harris type conditions, which are, so we define another norm, which is a norm adapted to phi 0, which is this. Okay, so this is a norm. And we assume that we have two conditions for Harris. We can prove that it exists alpha in 0, 1 and theta positive, such that for all f in L1, the norm of S tilde, okay, S tilde to the k, S tilde remind that it's this normalized operator is less than in L1, less than, or in L1 or in any norm for Banach space, alpha norm of f plus theta with this norm 0. And second condition, there exists a larger than alpha theta or 1 minus alpha, and there exists g in L1 plus not 0, such that for all f positive, if the norm of f L1 is less than a, the norm 0, we have S tilde kf larger than 0f. Under these assumptions, we can prove that this result, I said that yes, this result is means that for n large enough, S tilde is a contraction in this space. We can prove the same result with these conditions, but with constructive arguments. So the constants c and zeta will be explicit in terms of alpha, theta, and this quantity. And it's important for future application. For instance, for the Floquet bundle, we probably need to have some not necessarily optimal constants, but at least the dependence of these constants on the parameters.
Okay. Okay, so thank you again.
Thank you.